Good morning. How's everybody? Okay, Glass, present slide. Oh, wait a minute. It's fun to pretend, right?
We're not cool enough to have glass.
You'd think we would be. Good morning. Welcome to our session on WebM, Demystifying Video Encoding. My name's John Luther. I'm the product manager at Google for WebM and for video technology in the Chrome browser. And this is my colleague and co-presenter, Frank Galligan, staff software engineer at Google, also working on WebM and Chrome. And they tell you to open with a joke, and my joke is my picture. Just look so sad about something.
You look orange.
I know. All right, so what to demystify? First, I'm going to just give sort of an overview of what WebM is and VP8. We're mostly going to focus on the video side of WebM today. And then, the reasons why WebM is a great choice for developers to do video in their apps. I'm going to give some examples of how to encode WebM video using FFmpeg, which is a very popular command line encoding tool used by pretty much every video service on Earth these days, including YouTube. So Frank will then do his part of the presentation on how to actually build WebM into apps using our open source libraries, libvpx, the WebM container library, which is our wrapper format, and libvorbis, which is our audio encoder. He will then, if everything goes according to plan, encode a video on an Android device, upload it to YouTube, where it will instantaneously appear to the world. And then I will just touch briefly on what we're up to next, which is VP9, which is our next generation video codec. And we'll have quick Q&A, and then we'll let you go to lunch. So, how many people know what WebM is? That's okay, that's good. All right, for those of you who don't, WebM is a high-quality, open, royalty-free alternative for web video. What does that mean? That means that it's three things. This is how we define WebM for consistency's sake. It's the VP8 video codec. Soon we're going to add VP9. Vorbis Audio, which is a royalty-free, very good audio codec that's developed by the Ziff Foundation. And it's a Matroska-based file container. What that means is the audio and video streams are contained in a Matroska file container, but we use a file extension, WebM, to differentiate it from other files, because we wanted any user agent or client, we want to make sure that when they receive a file of .webm type or MIME type WebM, that they can always know that it's going to be these three things, and later VP9 and Opus. So, benefits for developers. Why would a developer want to use WebM? Well, more than anything, of course, is the video quality. The VP8 codec was developed by a small company called Cont'd Technologies, where Frank and I came from. Google acquired Cont'd in 2010 and open sourced VP8 for the world. So if you look at the quality that VP8 can achieve, just sort of as a base to judge these things, 1080p HD video is obviously very difficult to transmit over networks because it's so many gigantic frames of pixels. But with VP8, we can achieve very good-looking, high PSNR, which is how these things are usually measured, 1080p at about 3 megabits. So, most residential consumer, internet connections nowadays, they're getting there to the point where people have a sort of predictable, at least, we would hope, 3 megabit connection. But you could even do 720 at lower than this. So that's one gauge of how you could judge it. Simplicity of design. So VP8 is unlike other codecs you might know of in that we design it to be completely compliant across any decoder. So if any valid VP8 stream that you create will decode and play back in any compliant VP8 decoder. So why is that different than other codecs? Well, other codecs, let's say for example H.264, they have different profiles that are defined. So H.264 baseline, H.264 main. This leads one to believe that those are intercompatible, but they're not. A main profile decoder cannot decode a baseline bitstream. They're essentially three different codecs or more. There's baseline, main, and high. So with VP8, you never have to worry about that. So if you have, for example, if you want to serve video to glass users as well as users on MacBooks. The glass users, glass only supports baseline. These support high profiles. You'd have to have different bit streams for different clients, and you'd always have to be doing user agent checking, what does this one support, and so on. With VP8, you don't have to worry about that. Because there are no profiles, there are no levels, which is another way that codecs are sort of defined by what's the maximum size, frame size of this video, bit rate, and so forth. We don't do B frames, which are kind of a way to predict forward and backward in the video. No IDR frames. We try to keep it as simple as possible, yet we do achieve the same quality as something like H.264 high profile. On the other side of the equation, the decoding, we try to keep it very low complexity, meaning that it's very important for us that VP8 run fast in software, even on lower power devices. I think a lot of times we in the Western world forget that not everybody buys a new computer every year or every even 2 years. There's still a lot of devices in the world that have a very hard time decoding other codecs and software. VP8 opens that world up to more users because it can decode on even lower power, older generation ARM processors, which there are still many, many of those in the world today. It's also very widely supported, so WebM as a format in the video tag in desktop web browsers. This is just some data I pulled from StatCounter. So native WebM, meaning you install the browser, it's WebM capable out of the box, is about 60% of browsers in use in the world today. So that means Chrome, Firefox, Opera, a browser that's built on top of Chromium. It's in the Chromium source. It's in Firefox, the Gecko stuff. Anyway, the light green segment is browsers that we can address with plugins, which are freely available and downloadable from our website. This is primarily IE 9 and 10 and Safari 5 and later. The gray slice is browsers that not necessarily don't support WebM, but just simply don't support HTML5 video, which is IE8, IE7, a lot of older browsers that are still out there in use today, but don't have the capabilities. So adding it all up, the dark green wedge is actually growing pretty fast over time. So you can be pretty confident that in some way your users will be able to play WebM. So also as I was curious about mobile. Tablets are obviously, becoming very important platforms for media consumption, playing video. So I wondered, okay, well, in the aggregate worldwide, what percentage of tablets support WebM natively? And it turns out it's about 43.4%. So this is obviously, a lot of this is Android. And as you heard yesterday in the keynote, Android is growing at a kind of a moderate rate, I guess you might say. So anywhere where Android grows, WebM grows because it's supported in the Android source repository out of the box. There's also more hardware coming online for VP8. This is a topic that everybody likes to discuss. VP8, hardware support is important to devices, low power devices especially, something that's not plugged into a wall. So if it has a battery, you want to conserve as much of that battery as possible. Doing video encoding and decoding operations in hardware is much, much less power intense than doing it in software. So anyway, a lot of that's starting to come on the market now. There are VP8 decoders coming to market. Pretty much every major SoC vendor, which is SoC, the ARM chip vendors who have there's an ARM core in the SoC, but then it has blocks for hardware operations like video and audio. Pretty much every major ARM-based SoC vendor is now shipping chips with VP8 decoding, and they're starting to come in the market in things like the Samsung Chromebooks, Nexus 10, Samsung Galaxy S4, those types of devices. So as an example of what I mentioned about the complexity, YouTube obviously wanted to support the Wii. There's many of those devices in the world, and a lot of users love them. They wanted to play YouTube video on them, but the problem they kept running into is due to some platform limitations that Nintendo puts in place, they couldn't access the hardware to do the video in hardware and then doing it in software. They had other limitations where the 264 streams didn't have the horsepower to play them back, and then in the 263 streams, they just weren't getting the quality that they thought the users deserved. So they said, what about VP8? We ported and optimized VP8 for that platform, and now every Wii client in the world gets WebM video, and that market is now open to all those users. So that's an example where the simplicity of the designs that we always strive for end up paying off in the end. So perhaps most importantly, WebM is free, and that means both senses of the word as people know it, beer and speech. We don't charge any money for WebM. VP8, Matroska, Vorbis are all royalty-free technologies, and it's all open source. We have the VP8 codec is in a repository on the webmproject.org website. Anybody's free to use it. It's under a BSD license, which is one of the more liberal open source licenses, means anybody can fork it. I've even had customers ask me, if I use it, do I have to still call it VP8? And you don't. You can call it whatever you want. That's the beauty of the BSD license. So why is this important to developers? It's important because other codecs can cost you millions of dollars a year, and that's not an exaggeration. A lot of standards-based codecs have royalties associated with them. It's nothing to do with the standards groups. They just assemble the technologies and write the specs. It's the people who own patents that are relevant to those standards that then form pools to charge royalties for them. The H.264 and VC1 royalty pools today have maximum annual royalties of $6.5 million a year. For apps, it's sort of a sliding scale, but it's basically 20 cents a unit of every app that you sell. So what does that mean to you? Let's say you're an Android developer and you have an app that you want to do video encoding like Frank's going to demonstrate. That app, let's say you put it in the Play Store and you charge 99 cents for it. 20 cents of every sale you make goes to a pooling organization called MPEG-LA, up to the cap of $6.5 million a year. This is even applicable if your app is free, because the royalty is to use the technology. It's not a share of the money you make or anything else. If your app just does content in those formats, let's say you are able to sort of take advantage of the codec that's in the Android platform SDK or hardware, if you're charging users any amount of money to consume that content, you're going to owe royalties as well. So none of this, thankfully, applies to WebM. It's all free, it's all open, anybody can use it and not owe anybody any money. So that's all the great properties of it. I'm just going to show you how to actually make one of these files. Who understands how video compression works? Probably most of you, right? Okay. The primary aim of any kind of compression, but particularly video, is to remove redundancies in data. With video, you have redundancies within frames of video. That's called spatial redundancy. Temporal redundancy is things that are similar in a sequence of frames. You can get rid of all that stuff. Statistical redundancy, redundancy in the data stream itself, the ones and zeros. Take those out. There's perceptual, it's called redundancy, but it's not quite. It's just things that the human eye can't even perceive. Just take those out. So you take all these things out with the ultimate goal of removing them, yet keeping the quality as close as you possibly can to the original source video. This is the art of the technology. How do you do all this, yet when you reconstruct the image from the compressed bit stream, what the user sees is, you hope, imperceptible from what you started from. So raw video right off of a camera, an editing deck, whatever, if you just have all those full pixels, it's not compressed at all, it's gigantic. So let's say this video that I'm going to encode is not even HD, it's around standard definition. It's 17 seconds long, just for the sake of brevity here, yet it's 320 megabytes, that file. So I don't know about you, but my network at home can't serve that data rate. I don't know, maybe if you had fiber, maybe, but even then, probably not. Audio, same case. The raw audio stream that I'm going to use, which is PCM samples, is 3 megabytes. Again, it's 17 seconds. So how are we going to get 323 megabytes of data over a network to a user in 17 seconds? Well, we're going to use FFmpeg. We're going to combine these streams, which is called muxing, multiplexing. We are then going to run them through FFmpeg, and this is represented by this clever spinning logo. This is where all that magic that I talked about happens. This is where the codec is going to look at these frames of video and look at all the redundancies and just pull them all out, compress it all down into a stream. And the final result is going to be a WebM file of 1.9 megabytes. So we took 323 megabytes worth of raw data, and now this is something that 17 seconds, 1.9 megabytes, easily can be served to pretty much any user, maybe even over a 3G connection. So let's look at how this is done. This is the example. I have a couple examples in the slide. You'll be able to download them later and play around with them yourselves. You can modify them. There are other options. You can go as deep into this stuff as you want. But one of the beauties of VP8 and WebM is that we have, again, with simplicity in mind, you don't have to be an expert in this stuff. You don't have to hire consultants to show you exactly every parameter required to do this. Pretty much if you put a video into the libVPX compressor, it makes a lot of the hard decisions for you. What comes out is, in most cases, pretty great. So let's just step through these parameters here. First is the binary, FFmpeg, that's the program. The .I is the input video. So this is, again, this is a raw stream, Y4M, just raw pixel data. Same with the audio, just a WAV file, PCM samples. This CV parameter here is libVPX. That's the library that we at the WebM project make available in source or binary from the website. Does all the VPX or the VP8 encoding magic. BV is the bit rate. So I'm going to set the target bit rate of this file to 800 kilobits per second. What does that mean? That means I tell the encoder, I say, okay, if you can encode any frame or segment or 1 second's worth of video in these streams with using less than 800 kilobits of data, go for it. That's great. Yet, don't exceed that, because my target use case, I know that my users, let's say I know from market research, whatever, that most of my users don't have any more than a megabit reliable connectivity. So with overhead and audio, I want to keep that well below 1 megabit a second. So I'm going to specify 800 kilobits as my target data rate. Quality setting is just, in the VP8 encoder, there's 3 settings, real-time, best, and good. Best and good are kind of misnomers in that, yes, best will give you the absolute best quality, but in most cases, good is just that, it's good enough, and it runs faster. The best quality will give you the best output, but it is, in some cases, depending on the material, can be significantly more intensive and take longer to encode. So this next is just a video filter, the VF. There are a number of filters that you can use in FFmpeg to do all sorts of things, like scaling is one of them. So I'm going to scale this video. Right now it's a little bit bigger than standard definition. I'm going to scale it down to standard definition, which is 480 pixels high. The -1 argument is I'm saying, okay, I want you to make it 480 pixels high, but the width, I want you to keep it proportional to the input, to that Y4M file. So this means that it's going to scale it proportionally. Whatever that width ends up being, that's what it's going to be. This prevents things like if you use the defaults, in some cases, it'll scale. If you just say scale 480, but you don't preserve the aspect, you get these videos with people stretched out or squished or, So in pretty much every case, you want to preserve the aspect ratio. The last arguments are just for libvorbis. This is the audio encoder, also freely available, and I'm just going to use the default settings there, which are good enough for this use case. And the last one is the output file, which is cleverly enough called w480.webm. So just like on the old cooking shows, through the magic of technology, I happen to have one of these already ready to go. So let's see what happens. Now, just spit out a bunch of scary looking stuff. It's not that scary. All it is mostly some information about how this particular instance of FFmpeg was compiled, all the flags and things. The interesting stuff here is this sort of purple text. So it's saying, okay, I see that you've handed me a raw Y4M file. It does some piping magic to handle those types of files. These are the properties of it. It's just telling me, look, you know, there are no time codes or anything here, so this might be inaccurate. I'm going to guess. That's usually good enough. Same with the audio. It says, okay, this is what you're handing me. You already have one of these files there because you've tested it in your hotel room this morning. Are you sure you want to blow that away? And I say, sure, let's go for it. So now the magic starts. All those things I talked about, again, with the redundancies, removing all these things that aren't needed to then that are not needed to reconstruct this image later using a decompressor. So you can see down the bottom, the final file size is growing. The bit rate in some sections is exceeding, but overall it's going to, across, the breadth of it should stay below. We're done. Okay. So let's see how we did. As I said, the aim of this is to make what comes out as close as possible to what went in from a visual perspective. So, we forgot to plug in the audio. Trust me, there's audio. And these screens, it's always hard. Projectors, the fidelity is usually not so great, but you can see this looks pretty good, right? This is only 800 kilobits a second of data, which Frank and I have been in this business for probably, long enough for you to get gray hairs in your beard. When we started in this, the idea of doing a standard definition video at 800 kilobits was preposterous. I mean, back then we were using 300 kilobits to do little postage size videos. So it's pretty remarkable how far the technology has come. Okay, so I have a number of these examples. I want to give Frank his time, so you can look through these later when you download. Just 2-pass, again, more quality, but it'll take longer. There's an example here of running the encoder in a real-time mode to make it run faster, which will slightly degrade the quality, but it will be done in real time. And then I just have an example here of how you would do this for a mobile use case. So there's lots of information on our site and around the internet. I put some links in here about using FFmpeg and some other things. And this is where I hand it over to Frank.
All right. Thanks, John. So John showed you one way to to encode videos on the desktop. I'm going to show you another method of adding audio and video encoding to your Android applications. I'm going to use a project called the WebM JNI Bindings. I have 2 demos, and then I'm going to take a little, time permitting, a little closer look at the code. So the WebM JNI Bindings allows your Android applications to interface with 5 open source projects. The code in the green boxes is the Java JNI code that your application will call. The code in the orange boxes is the C++ code of the JNI bindings. Most of the code in the orange box is just a pass-through from the Java JNI bindings to the C++ open source projects. There is a Vorbis encoder object class that makes it easier to add Vorbis encoding. Also has some specific functions for Vorbis with regards to WebM files. And all of the code in the green and orange boxes is what's comprising the WebM JNI bindings. The code in the blue boxes is the open source code that really does all the heavy lifting. It does the converting, does the encoding, does the muxing. And most of the code in the blue boxes is hand optimized for ARM as well as x86. Also in the JNI binding is the readme.android file. The readme tells you how to set everything up, where to get the open source codes, how to build them, and how to get ready to to add audio and video encoding to your project. So with that, we'll show our first demo. So what I'm going to do is I'm going to add audio and should be coming soon. Anyways, I'm going to add audio and video encoding to an Android device using the WebM JNI Bindings. I'm using one of the example functions from the bindings, which basically takes a raw video input, raw audio input, and outputs a WebM file on a device. What I did, I already created the new application. Here's the main activity file, which you probably all know. And I already downloaded the JNI bindings, set them up. I already downloaded all the dependent open source projects and set them up. I did that basically from the readme.android. Gives you all the steps how to do it, run through. It's pretty easy. We actually had a demo of when I tried to create a new project from scratch, download everything, add the audio and video encoding, and show the video file in under 5 minutes. It works sometimes, but we had to cut it because it was a little confusing and we didn't have much time. We're already kind of running a little late as it is. So I'm going to copy the code from the readme.android and add it to my main file on create. This is the code that will do the audio and video encoding. I will update my includes, and I'm going to set my video input file that I already pushed into my device on external storage. I'm going to set my audio file. Again, I already pushed. Save this, and now I'm going to switch to the Android device. So this is probably the simplest example. We're just reading the audio and video input file on the device in external storage and then writing it out to external storage. So let me show you that there is no WebM file on the device. Kind of feel like a magician. There's no cards up my sleeve. And now I'm going to run the application on the device. So it's a pretty boring application. It won't do too much. Okay, I agree. Oh, there we go. Like I said, it's not going to do too much. It'll either say success, it's done, or error, okay, good, success. So let's go back to the Explorer, hit refresh. Should have a WebM file. We can play it. So there we go. So it worked. It's nice when your first demo works, you know. You do it 100 times, it works every time, but you get up here and everything changes. So, all right. So now we'll go back to the slides. Maybe. All right. So now I'm going to go into a little bit of the code, the example code that I used from the Bindings project. The first set of slides is setting up the audio and video encoders, also the Muxer. You can see we're creating the libvpx configure object. We're passing in the width and the height of the source video. This is really important because libvpx will not scale the video, and at this point neither will the binding, so whatever you're creating on the input, it's going to be on the output. I'm also, in the example code, I'm showing setting the target bit rate to 1,000 kilobits. This is your most important setting. This is the setting you will always change depending on your use case for your application. For example, you could have creating a really small video, like 160 by 120 for whatever reason. You're going to set your target bit rate maybe at 100 kilobits. Or you could be encoding HD, and you set it at 3 megabits. Whatever it is, this is the one you're going to change. As John said before, a nice feature of libvpx is, for the most part, most of your applications, you're not going to be able to, you don't have to change the other settings. The defaults will be fine for 95% of the applications. If you do have a very specific need, there are other options, like if you need to set the keyframe target, if you have certain seeking requirements, or maybe the quantizer values, depending if you want to not go too high, the bit rate to not go too high or go too low. But for the most part, you set the target bit rate, and everything else is fine. Here, I'm just creating the Vorbis configure object. We're passing in the number of channels, sample rate, bits per sample of the audio. It's pretty easy. This code is setting the time base for both the VP8 encoder and the Vorbis encoder. This is really a convenience function because the Muxer, libwebm, expects the time base to be nanosecond units. And the only reason we're doing this is so we don't have to translate the timestamps later. If you didn't do this, the video default time base is milliseconds, and the audio default time base is samples per second. Oh, yep, and nanosecond units. Here we're just creating the encoders and passing config objects. Pretty simple. At this point, both the VP8 and the Vorbis encoder are set up. They're ready to start encoding data. The next few lines, we're setting up the Muxer. The first line is we're creating a writer object. And basically what that is it implements a very simple I/O interface. So if your application had different I/O needs, maybe you have a pack file, whatever it is, you can create your own writer object that implements the MKV writer interface, and you pass that to the Muxer. The default writer interface just uses the standard I/O, fopen, fwrite, fclose. Here we're telling it the file to write to, just a string with a path and a file name output. Oh, all right. And if you're writing to external storage on the device, you just have to make sure that you set the correct permission on your Android application. Otherwise, it won't work, and it might get a little confusing as why it's not working, but there it is right there. Here we're just creating the Muxer object, passing in the writer. Now we're adding the audio and video track. We save the track numbers for later. This is how the Muxer distinguishes between the different tracks as you pass it the track number. The first two parameters are both, I think, are pretty self-explanatory, same as the config objects. The third parameter to the add track is if you explicitly need to set a track number. For most applications, you won't need it. Passing in 0 to libwebm says, you pick the number, I'm okay with that. And the last part of this setup for the Muxer is the Vorbis audio needs some private data. So you have to set the codec private, which is basically what it says is it's data that's only interpreted by the codec. Again, if you use the Vorbis encoder from the orange boxes, it makes it pretty simple. You call codec private, it'll return the data in the correct format. You set it and you're good to go. All right. So at this point, everything's set up, and now we're getting into our encoding loop. I kind of have some pseudocode. I just say get the raw frame. The audio, the raw data is just an array of PCM samples. For libvpx, the raw data is either an I420 or a YV12 frame. I'll talk a little bit more about color formats when we get to the encode call. If the raw data is audio, it's pretty simple. We just call encode, give it the raw data, then we get the compressed frame. You see I'm getting close on time, so I'll try to go quick. For Vorbis, you have to check to make sure the encoded frame is not null because Vorbis needs a certain amount of input samples before it'll start passing back encoded data. First parameter is the encoded frame. Second parameter is the track number that we passed back from before. Timestamp, already in the correct time base. And the last parameter is a flag, a Boolean saying if it's a keyframe or not. All audio frames, all Vorbis audio frames are keyframes. If it's video, again, we pass the encode frame, I420. We also have another function call, because libvpx will only take I420 or YV12, but the libvpx wrapper will take some RGB color space as well as some other YUV color spaces, and what it'll do is it'll get the raw frames, send it to libyuv to convert it to I420, and then send it to libvpx. Timestamp duration has to be in the timestamp units. The libvpx encode frame returns an array of encoded packets. This is because the libvpx encoder can create what we call an alt-ref frame, which is basically a frame that must be decoded in order but not shown. We loop through the array of encoded packets. The only real difference at the end, we check to see if the libvpx packet is a keyframe, and then we pass that. Oop, hit the wrong button. And finally, we tell the Muxer segment to finalize segment, which basically will output seek points if you want them, which by default is yes. And it will also seek back to the beginning and update some header values so the file will be playable. Oh, man. All right. John, you want to go to, why don't you do your slides? I'll do the YouTube demo because it can take a little while.
This is where you can get all this code that Frank is showing. Oh, sorry. I didn't want to. Hello? Test. Back on. Got it? Hello? All right, anyway, this is where you can download this stuff. I'm just going to talk very briefly about VP9, which is our next generation codec. It's also free, open, don't charge any money for it. The sort of, the big point with VP9 is it achieves the same quality as VP8 and 264 high profile using up to half the data. Saw it during the keynote, Linus Upson demonstrated VP9 playing side by side with a 264 video, and you could see that the 264 data rate was up here, VP9 was about half. This will start rolling out in YouTube and Chrome in Q3 of 2013. We're getting pretty aggressive about rolling this out because everybody involved is pretty excited about the data savings. Bandwidth is still an extremely expensive business cost. People keep thinking that it's free or that it's going to become cheaper, but it never does. So anyway, there was a session yesterday. You can watch the video on YouTube later or download the slides from that, and that's all I'm going to say on VP9. And I'll get to the really exciting demo. Right. You can go to. So the YouTube demo, it captured video and audio from the camera and the microphone, pressed it in real time, then uploaded to YouTube. Just looking at waiting processing. If it comes up, maybe we can play it. Otherwise, we could take some really, really quick questions. If anybody has any, just step up to the mic. And then we'll also have Q&A afterwards, too. Yeah, you can find us afterwards.
Glad to hear you guys are from On2. I actually used the On2 encoder probably a decade ago to do some video for web.
Cool. Nice.
And great quality at the time. Question for you is, for people that are video producers, is it easy to integrate the encoder into something like, say, Sony Vegas on the PC or whatever's commonly used on the Mac?
Mm-hmm. We have direct show and QuickTime components for the encoder and decoder that plug into pretty much all those tools.
Hi, I'm a computer engineer, and for us, it's always beat into us that there's always a trade-off. And when you guys are talking about this, you're saying it's low CPU utilization, very good compression ratio, and it still looks as good. And it makes me wonder, like, what's the catch? And if there isn't, why isn't there one, and why have all the previous ones failed to do it as good as this does?
There's no catch. I mean, encoding video is a very expensive operation, right? So when we say it's low quality, it's high quality, low CPU, it's compared to what the other current codec is like.
Right, and the other thing is you are losing something in that the raw source has everything. Even like I said, that stuff that your eye can't even see. So throw all that out. Like in editing bays and people who do pre-production, they keep lossless versions of files around to do editing, but then once it's encoded, there's so much in there that you just really for the human eye to see or anything else, you just don't need it.
Thank you.
So, here, I think this is what we took. So hopefully it'll.
Oh, look at kitty.
So we had a little Easter egg too. We had to show the little cat that we overlaid on the video before we upload to Encode.
I think we'd do one more question. There's also hats. It wouldn't be I.O. without swag, so anybody wants a free hat with a handsome WebM logo, see me afterwards. Sorry, go ahead.
Hi, name is Mauricio. I'd like to know how you see VP8 and VP9 being used for video calling in mobile devices.
Video conferencing?
used for video calling in mobile devices, either
Yes,
VP8
okay.
or VP9.
Yeah, I mean,
Part of the WebRTC, are you familiar with WebRTC? Yeah, we're trying to recommend it, or we have, as the mandatory to implement codec for WebRTC. It's what we're using with WebRTC at Google. It's one of the things that we had so little time that I had in an earlier draft of these gone into why VP8 is also a very, very good codec. Maybe in some ways better than for video on demand. Its real-time capabilities for RTC are pretty amazing. So the answer is yes.
So on the same line, one of the great things about the Opus codec, which you mentioned is coming in WebM, is its real-time performance. It's very, very low latency. What kind of latencies can you achieve with VP8 or VP9?
well, VP8, you can achieve sub-frame, sub-1 frame latency.
So like 8, 9, 10 milliseconds, kind of.
Yeah, I mean, it depends on your
60
options.
FIPS or
I mean,
30 or 24, right?
whatever options you pick, right, we try to keep it like 30 milliseconds or whatever, maybe 1 frame of latency. You can always turn off your options to get it to 8, 9, 10 milliseconds latency, but then your quality might not be as good.
Right.
So, we try to keep it to 1 frame latency. VP9, we're still working on it, but we have the same target.
Okay.
When it comes out, I think it's Q3 or 4 this year for
Q3. I mean, yeah, the bitstream is
for real time.
Yep, the bitstream will be frozen in June, and then
Yeah, for real time, it's Q.
Oh, for real time. I'm sorry,
Right.
Q4. Yeah, when we build into real time. They keep giving us more time, so I don't.
I don't know. Yeah, I don't know
It's
what
like it's
we're
running
doing.
backwards or something. So anyway, if you want a hat, come and see us. If you have any other questions, feel free.
And we'll be out
Get
at
us
the booth if
online.
you have
We'll
any
be
more
out.
questions.
Yeah, we'll be out at the booth. So thanks
All right,
everybody.
thank you.